Thanks.
For the record.
So thanks to the organizers for the invitation. I'm very happy to be here. And I'll spend the next half an hour telling you about a new project I have at UCL with some of my PhD students and a postdoc, Matteo Sammartino, who was here for a month, a couple of months ago.
Which of these four people are the PhD students?
So this is about automata learning. And what I'm going to do for the first 10 minutes or so is kind of describe to you the most well-known automata learning algorithm called L-star. But before I start, let me make some distinction about what I'm going to be talking about, which is called active learning, and something that is also very popular in the literature at the moment, which is called passive learning. So the idea behind active learning is that you have a system, a black box system, and you can query it actively. So you can ask, at any step, you can ask any question about membership. The idea behind passive learning, and there are various algorithms for passive learning, is that you record the behavior of a system for a couple of days or hours or whatever. You have a log, and then you try from the log to infer a model that approximates what the system does. So for the rest of the talk, when I mention learning, I always mean active learning. And active learning started back in the 80s with this paper by Dana Anglin called Learning Regular Sets from Queries and Counterexamples. And she described an algorithm in that paper that is nowadays referred to as L-star algorithm. In that paper, she looked at regular languages, and she looked at the problem of learning a minimal deterministic automaton that accepts a certain regular language. And you might think that this is kind of lame, because regular languages are so simple. But the reality is that the algorithm itself is also very simple, which makes it very beautiful, in my opinion. But it turns out it's also very powerful. So Anglin's algorithm was used mainly in linguistics for many years. And in the last, I would say 10 years, 8 to 10 years, it was rediscovered in computer science in the context of verification. And even though it's only about regular languages and deterministic automata, people managed to use Anglin's algorithm to actually verify protocols running in bank cards and passports and so on, and drivers in printers. So, you know, the fact that it's simple does not mean you cannot actually do real verification tasks with it. So here's, I'm going to show you L-star by example, and the setup is as follows, and this is kind of the setup for any active learning algorithm. There's this entity called a teacher to whom you can ask questions, and there's a black box system that you want to learn, and this teacher knows about what the system does. And what you're going to build an automaton model of the system. So if the system does more than regular queries, what you're going to build is kind of an approximation of the regular part of the system. And what you can ask the teacher are two types of queries. One is called membership queries, and basically you can ask, is a certain word in the language? And the other one is an equivalence query. So at some point, you ask a bunch of questions, and then you convince yourself you know what the language is. And you can ask the teacher, is my hypothesis actually the language that is running in the system? And the teacher will either say yes, or it will say no and give you back a counterexample. So this setup of having a teacher is an ideal setup. And as you can imagine, in actual verification tasks, you won't have a teacher. I mean, it's a black box system. You don't know what's running in there. So membership queries are easy to implement. Equivalence queries are not so easy to implement. So what happens with equivalence queries in a lot of the implementations of L-star that actually are doing verification is that you kind of approximate your equivalence query by exhaustive testing. So you kind of say, okay, if I query the system up to a certain length and it's matching what my hypothesis, I will say it's okay. Otherwise, you will find a counterexample, and that's what you give back to the user. So the algorithm builds not really an automaton directly, but it builds so-called observation table. That is basically a table that gathers all the membership queries you've done so far. So the idea is you have this table which is indexed by a set of words both on the rows and the columns, and every 0 and 1 that you see here on the table is basically populated with a membership query to the teacher, and it will have a 1 if and only if the word that you can obtain from concatenating the row index with the column index is in the language. So here's an example of a table and how you would build an automaton from the table. So the basic idea of these tables is that the rows themselves will be the states of your automaton, and the transitions in the automaton are obtained by adding an extra letter to the row index that you see here. So like here, Q0 is the row of the empty word, and with an A, I go to Q1, which is the row of A, and with another A, I go to the row of AA. So this automaton has 3 states because those are the 3 rows that we see here, and they are the only 3 distinct rows in the whole table. I'll give you a simpler example in a moment, but this is just to show that from a table, you can build an automaton by taking as states the rows as final states, any row that has a 1 in the column for the empty word. So here you start seeing I'm making some assumptions. In particular, I assume that the empty word is always a column index. Otherwise, this would not be well defined. The initial state is the row of the empty word, yet another assumption. I'm assuming the empty word is also a row index. And the way I will build this table is basically by starting from the empty word and then increasing the length of the words and asking more and more queries. And then the transition function, as I said before, you take a row and you take a letter and you return the row indexed by the word you had before concatenated with this letter. Now, you might wonder, is this really well defined? Because I'm hand waving a little bit. Well, it is well defined as long as the table has a certain shape. And here's the shape I need the table to have. I need the table, so table is just a function of this kind for S and E sets of words. And I need the table to fulfill 2 conditions. One condition is it should be closed, meaning that if I look at the lower part of the table, so I will always draw the table with a line in the middle, which basically I have a, let's say, relevant set of words here, and then I have those words plus 1 letter continuation here below, which is kind of a 1 letter look ahead. And so if I look at the lower part of the table, so if I take 1 letter more than my, say, relevant set of words, then that row I obtained there brings nothing new. So there's already a row in the upper part of the table that contains the information I need. The other condition is I ask the table to be consistent. Namely, if 2 rows were the same in the upper part, then they should be the same after I take any 1 step. And this basically, these 2 conditions guarantee that the transition function is well defined. So first, this condition guarantees that actually the target state here, row of SA, is actually a state, because the set of states only contains rows that are in the upper part of the table. And the second condition basically says that the choice of representative I'm making here is irrelevant. So no matter what I choose as the S here, it doesn't matter. So if 2 rows were the same, they will still be the same here. Okay, so let's now go through the algorithm and see what you really build. So let's take a very simple language, namely the language of, actually let's already instantiate it. Let's take this language, 2 words, AA, BB. This kind of very lame example. How many states do I need to accept this language? Rada, you want to guess? Does anyone know how many states will it take to actually draw an automaton to accept this language? 5. So actually, it's a very simple language. It only has 2 words. But if you want to draw a deterministic automaton that accepts it, you need 5 states. So it's not such a simple example in the end. And it will illustrate all steps of the algorithm. Basically, the algorithm starts as follows. It says, OK, let's ask the teacher what happens with the empty word. So we ask the teacher what happens with the empty word, and the teacher says 0, because the empty word is not in L1. And then at the same time, we always extend the table with one more step. So we ask about A and about B. So I'm assuming my alphabet only has letters A and B. So at this stage, we say, I think I know what the language is. Namely, it's the language that accepts no words. And at this stage, making an hypothesis is OK, because my table is closed. So if I check if the table is closed and consistent, it will be. So it is closed because the only row I have here is the row with 0, and in the lower part as well. And it is consistent because I actually only have 1 row in the upper part of the table, so I don't need to check anything for consistency. So at this stage, I make the conjecture that the language that I'm trying to accept is the empty language. And the teacher will say no, because AA should be in the language, and it's not in the language you gave me. So then what do I do? So the algorithm tells me if the teacher replies no, gives you a counterexample, T, and you should extend your relevant words with T and all its prefixes. So the algorithm makes no assumption about the length of the counterexample. So the teacher could give you any counterexample. In this case, there's only 2 that she can give. But, so at this stage, we build a larger table. So we make a few more queries, and we have now a new table. And this table is closed because I have the only 2 rows I can see, which is with 0 and 1. Let's go. But it's not consistent because now the row for the empty word and the row for the letter A are equal. But after one A step, they are different. So at this stage, we need to fix this. So the table is not consistent, so it's not good enough to make conjecture. So how do we fix it? So the algorithm says, OK, if it's not consistent, because you've observed a difference after 1 step, then just add this difference to the table by increasing the column indexes. So I saw a difference after 1A. So I basically extend here things with an A. So now I have here the value for AA and here the value for A. So now the row for epsilon and A are different. So they don't play anymore any role in consistency checking. So at this stage, I again have a table that is closed and it's also consistent. So at this stage, I can make another conjecture, namely that this is the language. And it starts to look a bit more interesting, but the teacher says, it's too bad, because BB, so BB stays here, it's rejected by your automaton, but it's in the language. So you need to fix that. So you go on, and you do a few more fixes. So we add a few. So the counterexample was BB. So we add the row B and BB. We fill in this table. We add the 1-step extensions. And now the table is still closed, but again, it's not consistent because the row of the empty word, again, and B are the same, but after 1B step, they are different. So in the same way as before, we need to add 1 more column. And now I make another conjecture, and I ask the teacher, and the teacher says, you're almost there, but BA, BB is still wrong. So let's see. BA, BB is accepted, and it should not be. So you see, the counterexamples can go both ways. So you can get words that should be there and words that should not be there. So you do 1 more step, and after 1 more step, which I'm not showing here, you actually arrive to the right automaton. This automaton is the minimal automaton that accepts this language. And the algorithm is done in a way that you always keep the automaton minimal for every hypothesis you make. And that's crucial for termination, because otherwise I could be adding states that are completely useless and the algorithm would never terminate. Okay.
Ask a question?
Yeah, sure, sorry.
The step I didn't understand is how you made the conjecture from the table. Like, why couldn't
This one?
you- Yeah.
From
For
this one to
example-
this one?
Yeah. Because you could make other conjectures for the information that you have so far, right?
So by definition, from a closed and consistent table, I build an automaton that accepts the same language as this table is consistent with. And the automaton is built in the following way. The states are the rows of the table, actually of the upper part of the table. The transitions are given by the one-letter extensions of the row indexes. And the final states are all the ones that have a 1 in the lambda column.
So he's right. You could make other conjectures, but this thing will give you the smallest.
Yeah, so this would not be minimal.
Consistent with the table.
Okay. Righteous.
I mean, you could make a conjecture that is still consistent with the table, but if it's fully consistent, it accepts the same language, right? And then either it's the same automaton or it's not minimal.
Well, I mean, like
So the way you keep minimality is by observing that these rows,
Right.
they really denote all the Myhill narrowed equivalence classes of your language. Okay, so this is L star by example. And there's lots of papers out there with applications and also some generalizations to Mealy machines and I/O automata and a few more things. But, so this is where things were till 2 years ago. And the thing is, people realize that finite alphabets are not enough in some applications. And so we started wondering if we could extend L star for infinite alphabets and how would that work. So let me kind of just illustrate what this means and where the challenge really is. So if you take this language that we used as running example, and you now assume that your alphabet is infinite, then the language will be infinite. So an automaton accepting this language will have to have an infinite number of states. And if you stare at it for a while, you will realize that, well, it is infinite, but in fact, you could come up with a finite representation as long as you allow certain variables in the states. Namely, in this middle zone here of the automaton, all these states here are somehow doing the same for a certain, if you fix the letter there. If you have an X there, then in fact what you do in the next step is fully determined. So this idea of equipping the automaton with, say, a couple of registers has also been out there in the literature, and it kind of increases the amount of examples that you can cover. So that's kind of the goal, to try to now to learn this type of automata. So this is, well, there's many ways to formalize what these automata really are. But what I'm going to use in this talk is what we call nominal automata. So I think many of you in the audience have seen this. So nominal sets were rediscovered in computer science by Andy Pitts and Jamie Gabay when they were studying, say, an elegant mathematical framework to deal with alpha equivalence and name binding in the semantics of programming languages. And the idea, I mean, nominal sets in a sort of a nutshell are infinite sets with symmetries. So they are infinite, but they actually are finitely representable, which makes them amenable to kind of have these finite representations like I showed in the previous slide, and I'll show one more in the next slide. So nominal sets were kind of there in this work of Gabay and Pitts. And then a few years ago, this group of people from Warsaw started looking at automata theory over nominal sets. So take an automata theory book and replace every set by a nominal set and ask the question, which theorems are still valid? So they have a series of papers on developing automata theory over nominal sets. So going back to that example, or a similar example to that one I had a couple of slides ago, consider the language of words where a certain letter occurs twice in the word. So how would you build an automaton that accepts this language if the alphabet is infinite? Well, one way to do it would be to say, start from S0, from some initial state, read letters. So A here is kind of a symbolic representation. This can be any letter, so it's not only letter A, but kind of read. And then at some point you make a guess that the next letter you're reading in S0 is actually the letter that's going to occur twice in your word. You make this guess, and at this stage you are in a state where you know that you can only accept if you see A again. So when you see A a second time, you accept. So again, we see this kind of structure that is infinite. I mean, this pink area here in the middle is an infinite number of states, but there's a pattern. So you can kind of write this down as a finite representation where this middle state has this kind of variable that you can change the name, and as long as you do it modulo changing transitions as well, this all will work out and will be an acceptor for this language. So formally, what this is here, you have 3 states. In fact, you have 3 orbits of states. So the initial and the final state are kind of the single state orbit. And this middle state here is really standing for the whole. So there's kind of one state for each. So it's an infinite number of states. There's one state for each letter in the alphabet, and the alphabet is infinite. However, modulo permutations, the transition function is closed under the permutation. So this is what is called equivariant. And that's what it's kind of the core behind the fact that you can represent this in a finite way. So this talk is basically, I want to show you how to generalize L star for nominal automata. And the way we developed this algorithm was using category theory and co-algebra. I will not be showing much of that, just a little bit. And we could have done that. So in the literature, you will find other types of automata that could be used to induce finite representations for the languages I've shown, namely what is called register automata or fresh register automata. And the reason why we decided to go with the definition of Mikołaj and others is that nominal automata, as they are presented by the Polish crowd, are just automata in the category of nominal sets. So in fact, what I want to argue, and this goes back also to a comment that was made during the discussion yesterday, is that a categorical approach to understanding algorithms is not only useful to understand why an algorithm is correct, but it's also useful to generalize algorithms to other structures. So in this case, what we did, and I'll show in a second, looks very trivial once you've understood the correctness of the algorithm using category theory. And then it's just between quotes, a change of base category. And this is what I think Bartek likes to call the lambda x nom x research program. So the real title of this talk is really lambda x nom x applied to L star. This is what I'll show next. Appears in our Popol paper of next year. And a lot of the categorical background was developed in the note I wrote for the Prakash Fest with Bart Jacobs. So take the algorithm as it was and wonder if you apply the Boyancic approach, what would you have to change to make this work in nominal sets? So you replace every set by a nominal set, and then you stare. So the first thing is the table, so the row and column indexes, are now infinite sets. The weakness is that you need to find to solve the fact that the table is not closed or consistent again, might require that you check an infinite amount of rows. And the counterexample you get from the teacher, so we're still assuming the teacher is a very concrete entity, so you get a concrete counterexample with concrete letters, so not symbolic. So T is a finite word, so it will only have finite prefixes. So this means that you are kind of the way you are extending your S is not really good enough, because you need to build an infinite state space. But the way you are extending it seems to only generate finitely many new rows. So there's a few things here that don't seem to be working. And we know for that language A, B, B, C, C, and so on, that no finite automaton accepts it. So this will just not cut it. However, here's what saves the day, is that because we are working in nominal sets, we know that actually those infinite sets, S and S extended with A and E, admit a finite representation up to permutations. So even though they are infinite sets, they are orbit finite. And the table, the function rho, is equivariant. So it will be the same modulo the permutation. So this means that the table itself should also admit a finite symbolic representation that operates only on a finite number of orbits. So, in fact, the algorithm, after you stare at it for a while, you realize that you can fix the algorithm by only changing 3 lines. One, when you extend S, you do not extend S with one word, but you extend it with the orbit generated by that word. So the word plus all the words that you can obtain by applying permutations. Same thing for the column, and same thing for the counterexample. So it seems that only 3 lines changed, and this is all very easy, and that's great. But it's not really, it's not really as trivial as I'm trying to make it look, because as I said, you change the base category, right? So all definitions need now to be talking about orbit finite sets instead of finite sets. And this, in principle, means you need to reprove correctness and termination and all the theorems that Angwin had in her paper. So have we really saved any work? And this is where category theory comes to play a role, and where things become simpler by using these techniques we developed in the paper that we had for Prakash's 60th birthday. So the observation is that the definitions of close and consistent, which are kind of the crucial definitions in Angwin's original paper, can be written, and the details don't really matter, but they can be written in a certain diagrammatical form that, after you look at it for a while, you realize that the requirements for these definitions are really only the fact that you have a category where you have epi-mono factorizations. And not only you can, first of all, you observe, once you draw these pictures in this way, the first thing that to me was striking is that you can really see that closeness and consistency are dual concepts. You can really see that from the diagram. And the second thing is you reduce your assumptions to a very kind of general condition. So this epi-mono factorization is something that exists in many categories. And why is this useful? Is that the moment you kind of come to terms with the fact that this works, you can take S to be an orbit finite set. I mean, you can transport these diagrams to nominal sets and things just work. So the definitions are the same, really the same. And more interestingly, the proof of correctness of the algorithm and termination, so actually termination in Angwin's algorithm is really the proof of correctness, is also the same. And it's also reduced to kind of a pretty butterfly diagram, which again works in any reasonable category. So from that, we had already observed in 2014 that you could learn a certain version of weighted automata, basically by changing the base category to vector spaces. There was a paper from 2009, which was not done categorically, was done very concretely, where they present an Angwin-style algorithm for NFAs, and in fact, it can be obtained from this categorical perspective by replacing sets by joint semilattices. You can also do a kind of improvement on L star that is known as Rivas and Shapir algorithm by learning something called product automata. But all of these things that were out there, including our own perspective on things, we were assuming the alphabet to be finite somehow. So once you move to nom, correctness is still easy because it's just a diagram from a couple of slides ago. It's very easy to implement variations because of the abstract perspective, and you can work in different data domains, which means you can implement even versions of timed automata. But not everything is easy. I mean, one thing one should not underestimate is that the correctness proof is the same, but then once you try to implement the actual algorithm, you need to represent all those infinite structures in some finite way. And so when we started implementing the algorithm, we very quickly hit a wall. I mean, this was really the tricky bit. And the problem was there was some sort of, we didn't really have a good programming language with nominal support. Gladly, the Polish crowd was already working very hard on doing this, and they even have 2 programming languages now with nominal support. So we teamed up with them and used the algorithm as sort of a proof of concept for one of their extensions of Haskell, and which meant the implementation was not very efficient. But one thing I would like to say, which was for us, it was very neat. So we had an implementation in Haskell of the original algorithm. Then we copied it and pasted it to this Haskell, nominal Haskell extension, which is called n lambda, and it was running. It was literally running. Copy and paste the same code. And again, it's the same code, but the base, the basic computational model is different. And it was just running. It was just not efficient at all, but it was running. The only thing that turned out to be kind of the wall then, even after we had some sort of support, was that the nominal language that Bartek developed with his students was very targeted at the nominal support, and they kind of forgot that to talk with the real world, you need concrete communication. So you need concrete counterexamples. So in the Popol paper, we had to kind of hack the concrete communication. And by now, this has been fixed. So actually, we've been using the algorithm and the verification tasks we want to do with it as a sort of driving force to get the n lambda library a step further. And there's also a C++ extension with nominal sets, which we, in the meantime, have implemented the algorithm in. And surprisingly, it's not more efficient than n lambda. And this is, of course, probably due to the fact that they haven't really improved their library very much. But for now, we're still sticking with the Haskell extension. So I guess the message is that this abstract perspective gives you some guidance in developing algorithms, but in the end, you still, if you want to implement them, you still need to do some work. Okay, so I'm going to skip this. We are now actually using the algorithm to learn real protocols and actual code. And this is kind of last week and this week's work. So it's really ongoing work. And I'm just going to skip it. It's basically what we're trying, and this is current work. We want to test the algorithm in actual protocols where this nominal setting brings something new. So protocols in which new names have to be generated, which are kind of pervasive in crypto, seem to be kind of the good testing suite for this. We have implemented in the meantime concrete communication with real code. So we're really getting to a point where we will be able to perform some verification tasks. So maybe someone in the audience here has some more examples that we could learn with this new algorithm. A bit more future work. Let me focus a little bit on this, because this is something I came to think of by a remark of Gordon, who's probably in the audience. And it actually, I think, is actually one of the neat theoretical things that came out of the work. So when you're learning these automata, they very quickly, so we tried, as examples in our POPL paper, we tried to learn simple data structures like FIFO buffers. And when you start learning FIFO buffers, you hope you make it to FIFO5. And it took us a couple of weeks to make it to FIFO5. So I mean, you could learn automata that represent a FIFO2 very easily, a FIFO3. But the moment we hit FIFO3 with the original implementation, we were stuck. And that was very disappointing. I mean, you cannot submit a POPL paper with a FIFO3 because this is, I mean, it just says something about your implementation that you don't want the reviewers to know. So we thought hard what was going on in the algorithm that was kind of, why was it so inefficient? And then we realized that the tables we were building were growing very, very fast. And most of the time, there was a lot of redundant information in the table that we did not want to have. So we very quickly realized that this was a phenomenon that we had seen. Namely, take the language of words where the fifth letter from the right is an A. This is an example in most automata books to show that if you try to build a deterministic automaton for this language, you will need at least 32 states. But there's a very obvious 6-state non-deterministic automaton that accepts this language. So we very quickly realized that what we should be doing would be to kind of be storing the table as a sort of non-deterministic automaton. And this would mean that we could learn more languages. And as we were doing this, and this is already in the literature for the original L-star algorithm, so other people have observed this, we realized that this phenomenon of sort of a succinct representation of languages is more general than just non-deterministic automata versus deterministic automata. Actually, you can do this for any monad, or let's say for a large class of monads. And in the case of nominal automata, what was very interesting is we realized that a lot of the table was growing due to non-determinism, that's one point. But also the other point was that there was a lot of redundant information that could be compressed if you allow a sort of substitution monad. That is, it is a sort of introducing more alpha equivalence than you already have. And again, we proved correctness of that concrete example using the same techniques. So we now believe that there's a more general theory out there to be discovered. And not only we believe, we are pretty sure, because recently we discovered that Arbib and Manes already had a paper from '74 where they argue a similar thing for a class of monads. So that's kind of one of the exciting line of work that came out of it. But definitely, real verification tasks and the implementation is what's keeping the students busy at the moment. So that's it. I'll stop here.